Welcome to video 4. This is the next video in the series, and in this video we're going to be working with the perfect complements utility function. We're going to look to do two things in this video. We're going to do some optimal choice analysis, and then once we've got a handle on that, we're going to turn our attention into deriving demand functions for each of the goods in our utility function. So if you recall, perfect complements utility can look something like this. This is just one example, but we'll work with the most basic version of perfect complements where utility is equal to the min of x comma y. So in this example, we're looking at something that the consumer likes to consume together. So for example, we might have x as cups of coffee and y as scones. So the idea is here I'd like to consume cups of coffee and scones together. So let's go ahead and start our optimal choice analysis by sketching in some indifference curves. So I'm going to draw in my axes. Now you may recall that a trick that we can use in order to locate where all of the corners of the indifference curves might be is to take and set what's on the left-hand side of the comma inside the brackets and ultimately set that equal to what's on the right-hand side of the comma inside the brackets. In other words, the line y equals x is going to help us to describe where all of the corners of the indifference curves that we might sketch in will be located. So that's actually going to be the 45-degree line, or y equals x. So if we wanted to sketch in a specific indifference curve, let's suppose that we wanted to sketch the u equal to 20 indifference curve. Again, what we're looking to do here is find all of the pairings of x and y such that the number that gets spit out of the utility function is 20. So if we had 20 and 40, the smaller of those two, or the minimum of those two, would be 20, because x is 20 and y is 40. So there are three different points that we might want to locate on our indifference curve. And so there's our u equal to 20 indifference curve. Now again, you'll notice that the corner point is something that is going to be found by looking at the y equal to x line. And so that corner is right at 20 and 20. While we're at it, let's sketch in one more indifference curve. I'm going to sketch in the u equal to 10 indifference curve, just so that we've got another one to look at while we're doing this. And let's also start thinking about our optimal choice analysis. So let's suppose that we've got the price of good x and the price of good y both equal to $1. And let's also assume that we've got $40 to spend on coffee and scones. That means our budget constraint would be $1 times x plus $1 times y equal to $40. So the question we would want to ask ourselves is, how can we find our consumer's utility maximizing bundle? Now you may recall from an earlier video or from what we've discussed in class that in order to use Lagrange's method to do optimal choice analysis, we need for two things to be true. First, we need for the utility function to be differentiable. And then second, we need for the utility function to exhibit well-behaved preferences. And if you recall, what that means is that we need the indifference curves to be downward sloping, and we also need for the indifference curves to display a diminishing marginal rate of substitution. Well, clearly here with perfect complements, we run into a problem right off the bat because the utility function is in fact not differentiable. So we can't use Lagrange's method. On this slide, I've reproduced the graph from our previous slide, and what we now want to think about is, since we can't use Lagrange's method, is there some other way that we could get at finding the consumer's optimal bundle? Well, let me sketch in that budget line. It's going to give away the answer, but it'll help us to talk through the way that we're going to solve this problem more generally. So remember, as we're thinking about maximizing our utility, we need to stay on our budget line, and we want to reach the highest indifference curve we possibly can. So let me label a few points here. So I've labeled points A, B, and C. Now you can see from looking at the graph that bundle B is actually on the highest indifference curve. It's on the U equal to 20 indifference curve that we had sketched in earlier. Bundles A and C are on a lower indifference curve, and so those are not going to be our best choice. So let's stop and think about what exactly it is that's happening at either bundle A or bundle C. Now you'll notice at bundle A, I've got 10 units of good X, in other words 10 cups of coffee, but I have a lot of additional scones. So I have, looks like somewhere in the neighborhood of 30 scones to go with my 10 cups of coffee. But you've got to remember, my preferences are such that I like 1 cup of coffee to go with 1 scone. So the fact that I only have 10 cups of coffee but 30 scones, those extra scones just don't provide any additional utility for me. And so what ultimately that leads to is, if I'm purchasing bundle A, I'm spending a lot of money on scones that doesn't increase my utility. If we flip our attention over to bundle C, on the other hand, well, now I've got a lot of cups of coffee, looks like about 30 cups of coffee, but I've still only got 10 scones. And so the story is a very similar one. I'm spending money on cups of coffee that don't increase my utility. So what's happening at bundle B then? Well, at bundle B, we're spending all of our money, but we're spending it in a way where we're ultimately pairing things up in exactly the way that we like to. We're spending our money so that we're getting 20 cups of coffee and 20 scones. And the intuition behind this ultimately is just this. We want to choose optimal bundles that are going to be on the corner. If we ever spend money on either additional cups of coffee or additional scones so that we end up out on the arm of an indifference curve, well, we're going to have wasted some money. Since we don't want our consumer wasting money, what we'd like to do is solve our optimal choice problem to ensure that our consumer is always at a corner of an indifference curve and that she's spending all of her money. Well, if you recall, we actually have an equation that describes all of the corners of the indifference curves, and I'm going to label this equation 1. That equation was just y equal to x. Remember, every single corner of an indifference curve has to fall on that line y equal to x. The second piece is the budget constraint. We want to make sure our consumer is spending all of her income. And so in our optimal choice analysis, the price of each good was $1, and our consumer had $40 to spend on coffee and scones. Well, we've got 2 equations now, and so we can simply solve these together. I'm going to plug equation 1 into equation 2. So as I do that, I've got x plus, now y is equal to x, so I'll have a second x, and that's equal to 40. So that leaves me with my optimal choice of good x being 20, which we were able to see visually, but now we've confirmed that mathematically. Now if I go back to equation 1 and I plug in my optimal value of x, that just confirms mathematically what, again, I always knew graphically, namely that my optimal quantity of y is also going to be 20. So just to recap what we've managed to do here with our equations that we've set up, equation 1 and equation 2, we have found our consumer's utility maximizing choice for both goods x and goods y. In the next slide, we'll turn our attention to thinking about how we can do this more generally, in other words, how we can derive demand functions when we have perfect complements utility. In this slide, we're going to build on what we've just done with the optimal choice analysis. Our goal here, though, will be deriving demand functions. So I'm going to keep our perfect complements utility function exactly the same as it was. Here, again, we're trying to find optimal bundles for our consumer. Keep in mind, when we talked about transitioning from optimal choice analysis to deriving demand functions, all we're really doing in deriving that demand function is giving ourselves a general recipe for optimal bundles for goods X or goods Y respectively. So here we want to maximize utility for our perfect complements utility function, and we want to maximize that utility subject to our general budget constraint. However, we're going to run into exactly the same issue that we did with our optimal choice analysis. We can't use Lagrange's method. Instead, what we're going to have to do is make use of that insight that we had in the previous slide, namely that our consumer is always going to be maximizing utility when they're on the corner. So what we'll do is basically set up two equations here. The first, exactly the same as what you saw on the previous slide. The consumer is always going to maximize his or her utility along this line, y equal x, because that line describes all the corners of the indifference curves. In the upper right-hand corner, I've sketched in our u equal to 20 indifference curve from our previous example, but we could sketch in as many of these as we want. And again, the idea is that the corners are always going to be at the point where the quantity of x and the quantity of y are equal. So that's our first equation, y equals x. Our second equation is going to be very similar to what we did in the previous slide when we had been working with optimal choice analysis. But here, we don't actually want to plug in the values for prices and income. We just want to leave this in the most generic notation possible. So that's my budget constraint, and I'm going to do exactly what I did in the previous slide. I'm going to plug equation 1 into equation 2. So I'll have px times x plus py. Now, py times y is the term in the budget constraint, but y is equal to x, so I'll substitute that in. So I've got py times x, and all of that's equal to I. Well, now I can pull the x out so that I've got x times, in parentheses, px plus py, and that's all equal to income. And if I move things around one last time, I'm going to divide both sides by px plus py, and you'll notice the result that we get here. X is equal to income over the price of good x plus the price of good y. That's the demand function for good x. Now, there are a few things you want to notice about this demand function for good x. Unlike the work that we had done with the Cobb-Douglas utility function, you'll notice that the price of good x and the price of good y are on the right-hand side for this demand function. So what that's telling us is that the demand for good x is dependent not just on the price of good x, but also on the price of good y. So in our example, we had been talking about good x being cups of coffee. This tells us that our demand for coffee depends not just on the price of coffee, but also the price of scones. And as we had seen in our previous examples with Cobb-Douglas utility functions, we see income on the right-hand side. A key takeaway from all of this, though, is we're simply looking at a demand function. This is an intermediate micro-style demand function where we have income and the prices of both goods on the right-hand side. I'll let you do the algebra on your own, but you'll notice that if you go back and use equation 1 and equation 2 a second time through, you can also solve for the demand for good y. What you're going to notice is that the demand for good y ends up being exactly the same as our demand for good X.